All right, ladies and gentlemen, today we're going to be building on what we were talking about in the previous video, the remainder theorem. And what we're going to do is we're going to take an extension of what the remainder theorem said and develop something known as the factor theorem. And what that basically is telling you, from the remainder theorem, we said, well, if I substitute or if I do division with a factor and that remainder that we wind up getting from our synthetic division, if we substitute it back into the original function and evaluate it, we should get the same number. Well, that's really interesting because the solutions to a function, a polynomial function that we've been working with, the solutions happen to be when x is equal to 0, or we want to know where does it touch the x-axis. And that's one of the things that the remainder theorem leads us into here with something known as the factor theorem. We want to know where would a polynomial function touch the x-axis, meaning what are the zeros, what are the, pardon me, what are the solutions? So what we see here written for us, if we have some function f that's a polynomial function, and we have some factors, or some factor at least to start off with, if that produces a remainder of 0, or if I substitute the solution of the factor into the problem, into the function, and it simplifies to be 0, well, then that means it is a factor of the polynomial function, which will allow us to see where does it touch the x-axis, which allows us to evaluate it and graph it and do a whole bunch of other things with it. Okay, and this is pretty much kind of what I was just explaining. So make sure you get that copied down into your notes. And again, it's just if the function, if the solution to the factor gives us a 0 when we substitute it into the problem, that's essentially telling you that it is a factor of the polynomial, whatever you start off with. So here we have a third degree polynomial. It's third degree because the largest exponent is a 3. And we have two factors. And what we want to do is use synthetic division to see, do we get a remainder of 0? Because if we get a remainder of 0, that tells us that the factor that we're dividing with is a factor of the polynomial itself, meaning it would, we could use that to break it down into something more simple and identify what maybe some of the other factors would be as well. And again, we would utilize this information to help us be able to graph a polynomial, which we will be doing in the upcoming weeks. But let's go ahead and take a look at how we're going to approach a problem like this. So we have this third degree polynomial, and we have two factors that we're going to look to see. Do these two factors produce a 0 when we do our division? So looking at the polynomial, there's no missing exponents, so there's no 0 placeholders at all that I need. So I'm going to have coefficients of 1, positive 2, negative 11, and negative 12 for my constant. And I'm going to be dividing those. If I take this x plus 4 factor and I solve for x, set it equal to 0 and solve for x, that means I'm going to get a solution of negative 4. So let's go through our synthetic division process. Bring down the 1, multiply, and that gives me negative 4 here. Add those, negative 2, multiply, and I get a positive 8. Which, when I add those, it gives me a negative 3. Multiply again, and I get a positive 12 here, which gives me a remainder of 0. So what that tells me is that x plus 4 is a factor of that third degree polynomial. So now let's see, does it work the same for the second factor that we have here? So if I set this factor equal to 0 and solve for x, I'm going to get a positive 2, and we're going to divide that into the same thing. So 1, 2, negative 11, and negative 12. So let's go through our division process here. Bring down the 1, multiply, and it gives me a 2. Add, and I get a 4. Multiply again, I get an 8. Here I get a negative 3. And 2 times negative 3 is a negative 6, which gives me a remainder of negative 18. So because the remainder is not 0, we would say x minus 2, x minus 2 is not a factor. Now, from previous discussions, we have identified that because the largest exponent here is a 3, there should be 3 solutions. Well, since x plus 4 is a factor, then that means x is equal to negative 4 is a solution to the polynomial. So I want to know is what would the other 2 solutions be? Could we figure that out? Now, if we look at the quotient that we got here, if we wrote that out as a new function, well, remember when we do our division, we've essentially divided an x term out of the cubic polynomial that we started with. So this would wind up being written as 1x squared minus 2x minus 3. And can we factor this? And we absolutely can. So I can factor this into being an x minus a 3 and an x plus a 1. So these 2 factors would make up the other 2 factors of the polynomial, meaning that we started off with x cubed plus 2x squared minus 11x minus 12. Well, that would be equivalent to saying x plus 4 times x minus 3 times x plus 1. So on the left, we have it in standard form, and on the right, we have the exact same thing in factored form. Now, the advantage of having a function written in factored form is that it allows us to figure out what are the solutions. Well, if x plus 4 was a factor and it gave me a negative 4 as a solution, then I can also say, looking at the other 2 factors, that positive 3 and negative 1 would also be solutions of the function. So that way, if we were to graph this function, we know it would have to touch the x-axis at a negative 4, a positive 3, and a negative 1. And all of that information is helpful when it comes time for us to be graphing these. So here, let's take a look at our last example. We have another third degree polynomial, which essentially is telling you that there should be 3 solutions. Now, they don't always have to be real solutions. They could be imaginary. But for a third degree polynomial, we will for sure have at least one real solution, because imaginary solutions always come in pairs. So I could have one imaginary I could have one real and 2 imaginary solutions, or I could have 3 real solutions like we saw in the previous example. So here, they're not giving us a factor. They're giving us a solution. They're saying x is equal to negative 3 over 5. Well, the factor that would have produced a negative 3 over 5 would have been 5x plus 3. If I set 5x plus 3 equal to 0 and I solve for x, I wind up getting x is equal to negative 3 over 5. So they've taken a little bit of the work away from us. We don't have to actually figure out what is the solution that we're trying to do our division with. They're just giving it to us. Now, some of us may be hesitant a little bit simply because we're going to be doing math with a fraction, but again, it's just a number. Don't let it intimidate you. You're better than a number. So take the coefficients of the polynomial. So we have 5, positive 13, negative 9, and negative 9 for the constant. Go through the process. Bring down the 5. Well, negative 3/5 times positive 5 is a negative 5. Okay? I'm sorry, not negative 5. What am I thinking? It's negative 3. I'm thinking about trying to eliminate the denominator, and instead I wrote the denominator. So that will be a negative 3. If I add those 2 numbers together, I get a positive 10. So negative 3/5 times a positive 10 will give me a negative 6. So if I add those 2 numbers together, you get negative 15. Multiply the negative 15 to the negative 3/5, and I'm going to get a positive 9. So in this case, the solution of negative 3/5 is a solution of the polynomial. So this means that the 5x plus 3 is a factor of the polynomial. So First of all, we're trying to determine, is this a solution? Yes, it is. What would be the factor? The factor would be 5x plus 3. Now we can extend it just a little bit further, because if again I take the simplified, or rather if I take the quotient of the division and I write it as a simplified polynomial, I'm going to get 5x squared plus 10x minus 15. And this is another problem that I would say, well, could we potentially factor this? And absolutely we can. Now, again, some of these are going to be factorable. Some of them we may have to solve with the quadratic formula, but we can do a lot of stuff with a quadratic function like we have here. Each term has a 5 in common. So I'm going to go ahead and factor out a 5 to make it a little bit easier. So I'm going to have 5x, or 5 times x squared plus 2x minus 3 is equal to 0. And now I'm going to factor the quadratic inside here, and that's going to give me x excuse me, plus 3 and an x minus a 1. So these would be the other factors of the cubic polynomial that we started with. So if we wrote out the polynomial that was given to us, the 5x cubed plus 13x squared minus 9x minus 9, we could write its equivalent factored form that said the factor that we were given was 5x plus 3. Well, they didn't exactly give it to us, but we were able to figure out what it is. And then we would have the x plus 3, and we would have x minus 1. This standard form and this factored form, they're equivalent to each other. If we typed those onto a graphing calculator and hit enter to see what the graph would look like, they would produce the exact same function. They would produce the exact same graph. So again, the advantage of it being in factored form is it tells us a couple things. It tells us, first of all, what types of solutions we're going to be able to get, whether they're all real or some real and some imaginary. It tells us where the function has to touch the x-axis, and from there it will allow us to graph it relatively simply. So the solutions we can figure out from the factored form. So in this case, x has to equal the negative 3. Oops, I don't know why I'm writing a comma here. Let me clean that up. Getting ahead of myself. The negative 3/5 worked out to be a solution. That was what was given to us. But the other solutions from the other two factors that we figured out would be a negative 3 and a positive 1. So there's a lot of information that we can figure out based off of taking what we started with the factor theorem. I'm sorry, with the remainder theorem. Using an extension of the remainder theorem, we can say, okay, well, if I get a remainder of 0, then that must be a solution to the polynomial that we started with. And with that information, we can therefore break it down even further to identify even more solutions. And we're going to be doing this quite a bit as we move forward, talking more and more about polynomials. But I hope you guys took good notes, and if you have questions, please make sure you write them down and bring them to me in class, and I'll be happy to discuss them with you. And thanks for watching, and see you soon.